Hi, everybody. I'm really excited to be here in Russia. My family originally comes from Russia, so I've always wanted to come. And my old boss, Hartmut Kaiser, he went to school in St. Petersburg, and he always told me that this was just such a beautiful city. And if he watches this video later, he won't be happy with this, but he's kind of a grumpy guy. He doesn't like a lot of stuff. And when I told him that I was coming here, I asked him for some suggestions, and within like an hour, he sent me like an essay, like at least 2 pages of things that I should do in the city. And I'm like, wow, this guy really likes this city, and he doesn't like anything, so it must be pretty great. So my name is Bryce Adelstein Lalbeck. I work at NVIDIA. I lead the CUDA C++ core libraries team there. I'm also on the C++ standards committee. I chair the Library Evolution Incubator group and the tooling study group. But before I was a library person on the committee, I was primarily in the concurrency study group there. That's where I've spent most of my career, is writing concurrent code, building parallel runtime systems. And so this talk is sort of going back to my roots in a way. But before we get to the talk, I want to talk about something that I think is even more important. Before you can solve a problem, you have to recognize that you have one. And so as a leader in the C++ community, I want to publicly acknowledge that C++ has a diversity problem. We have a group, Include C++, that's a great group of people who are working to solve this problem. And if you're interested in learning more about diversity in C++, what you can do to help, go to our website, includecpp.org, and we have a Discord server. All right, so what is this talk about? This talk is about a bunch of new concurrency primitives introduced in C++20. You might be thinking to yourself, why do we need new concurrency primitives? Because we had in C++11, we had the introduction of a threading library and a bunch of synchronization primitives, most of which people who've written concurrent code are probably familiar with: mutexes, condition variables, atomics, etc. So we have these things. Why do we need new versions of these things? Well, to understand that, you have to think about the era in which C++11 was developed. That was sort of the start of the multi-core era, right? When there was this novel idea that we would have to deal with like processors that had 2 or even 4 cores. Like, this was a whole brand new world. And since then, things have changed. Now pretty much all processors are parallel. And they don't just have 2 or 4 cores, they tend to have a lot. Many of us are dealing with hundreds of threads, or in the case of people like me who work at companies that make GPUs, hundreds of thousands of threads. And so we're working at a different scale. And a lot of the traditional concurrency primitives in C++ today, they're not super suitable for that scale. So all the stuff that we're introducing in C++20 is designed for the current massively parallel era. And that's why we've introduced all these new features. So in this talk, I try to use as many C++20 features as possible. So I'm going to use ranges in a bunch of places, but unfortunately, ranges, the ranges facilities are mostly in nested namespaces. So here are 2 namespace aliases I will use throughout the talk to make my slides, smaller. So std_r will be the std ranges namespace. std_v will be the std views namespace. So when I was thinking about how to do this talk, I was thinking, well, okay, I'll just do this sort of the traditional way. I will go through each feature, and I'll show you some examples for each feature and explain each feature. But then I thought that's actually kind of boring. I wonder if I can build one long like little demo or example that uses all of the things that I want to show off. And once I started thinking about that, I came up with a particular idea for what I could do. And that idea was to build a little tasking runtime and then some parallel algorithms on top of it. So this is something that I did many years ago. I worked on a parallel runtime called HPX. So this talk is basically how to build an HPX in 2,000 lines of code or so. So there's four main components that we need for a tasking runtime. First of all, we need some threads that are going to execute our tasks, so some group of worker threads. Then we need some sort of work queue, which the worker threads will get their task items from. Then we need some mechanism of telling the worker threads when they're done. This is actually a good bit trickier than it sounds. And then we want something useful on top of this, so we'll build some parallel algorithms that uses this machinery. So let's start off by talking about the worker threads. So first, let's create some little facility. We're going to need a couple of these, and we're going to want each one of these worker threads to be executing the same thread function. So let's create this thread group class here. It's just going to have a std vector of std threads, and in its constructor, it's going to take a number of threads. So how many threads should be in this thread group, and then it's going to take one function. This is using this std invocable auto syntax here. That's C++20 concepts, abbreviated syntax. So that means f is like this constructor is actually a template, and f is something that satisfies the invocable concept. And then we just construct one thread for each one that's been requested here. All right, so that's pretty simple. Then we go and we use it like this. So we create a thread group with 6 threads. We have each one of them just execute some task that increments an atomic counter here. But this has a bug, and the bug is that when you destroy the thread group at the end of this scope right here, right here, your program's going to blow up, because when you destroy a std thread that has not been joined, std terminate gets called. Std thread doesn't really have ray semantics. When you construct it, you get a thread, but when you destroy it, sometimes things blow up. It doesn't necessarily clean up the thread. And the reason for this is that we didn't want to, 10 years ago, we didn't want to have std thread block in its destructor, block pending the completion of the thread that it spawned. But this is a little unfortunate, because it means that if you don't forget to explicitly join your threads, like in the destructor of thread group here, we can just call for each on our vector of threads and then join them, and then we'll be fine. But if you forget to do this, then you might get unexpected results. So this isn't normally how things in C++ work. Usually we want things to clean themselves up when we destroy them. That's not really the case with std thread. So in we're going to go into another problem first. All right, so we're planning on using our thread group to implement a task pool. That means that each worker thread will be continuously executing some loop that processes task items until we tell it that it's done. So I'm using this while true loop that just increments a atomic counter as sort of a placeholder for what our actual work loop will look like. You know, we've got some while condition where the condition is, are we done yet? And then in the body of the loop, we execute tasks. So we need some sort of side channel to signal termination with std thread. So we could do this with something like an atomic. So in the main thread, we create an atomic bool. We initialize it to false. And then inside of the worker thread's thread function, instead of while true, we have while that atomic is false, we'll continue, doing our thing. And then when we want to shut down the thread group, we just store true to this atomic variable. So this is fine, this works. We could also do this with a condition variable. There's a few other ways that we can do this. But it's a little unfortunate that we have to do this as a side channel. This is a pretty common pattern where you want to spawn off threads, and then you want to give yourself some mechanism of telling the threads when they're done, or when they should stop. So in C++20, we have a new, better thread class that has ray semantics and a few other nice features called jthread. So jthread, it stands for joining thread, because in its destructor, it will join on the underlying threads, potentially blocking. So it's just like std thread, except if the thread is joinable, it joins with it instead of calling terminate in its destructor. So with jthread, we don't need that explicit join in the destructor of thread group. Like, this just works out of the box, and that's nice. So std jthread has another useful capability that std thread doesn't have. It's got an interruption mechanism. So when you have a jthread, you can call request stop on it, which will signal to the jthread that it is time for it to finish execution. And you'll notice here in this slide, instead of just a std invocable, which takes no arguments here, now we're taking a std invocable that takes a stop token. So our worker thread function can, with JThread, your worker thread function can take this stop token handle, and then you can query the stop token handle to find out whether or not the thread has been sent a stop request. So this little interruption API, it's both in JThread and it's in some of the concurrency primitives in the standard, and it's quite useful. So on a JThread, you can ask it for its stop source. We'll talk about what that is in a minute. You can ask it for a stop token, which, as I said, is a handle that you can query to figure out whether a stop request has happened. And then you can request that a particular JThread stop. So the actual stop mechanism, there's three components here. It's very similar to futures and promises and sort of to stood future and stood promise and sort of the overall design. So you have stood stop source, which is analogous to a promise that is the producer side of this mechanism. So it produces stop requests and it owns the shared state. So some shared entity that consumers are going to be hooked up to. And then you have stop tokens, which are sort of analogous to futures. They are a handle to a stood stop source, but they are consumer only. You cannot request that a stop token stop, but you can query whether a stop token has been stopped. And then you have this stop callback mechanism, which unfortunately we're not going to talk a lot about today. That's analogous to the concurrency TS v1's future then method. It's a mechanism that allows you to register invocables that should be run when a stop request is received. And if the stop request has already been received, then the invocable would be run immediately, of course. So as I mentioned, there are some of the concurrency primitives in the standard that have blocking APIs have had new stop aware APIs added to them. Unfortunately, not all of them have these APIs, and in particular, some of the new things we're going to talk about today regrettably don't have those APIs, which is a bit of a tragedy. It would have made some of these slides a little bit easier, but I suspect in C++23 that we should have these stop-aware APIs on all the blocking primitives in the standard library. So these are actually very, very useful because typically if you're waiting for some sort of termination signal, you can't really block unconditionally. But you have to block with some timeout or something because you need to go and check whether you've received your termination signal. With these APIs, that is done under the hood, which means that it might be done in some clever way on your OS where it doesn't actually have to be a polling API. So the idea here is like if I call wait until on a condition variable any with a stop token, it will wait until the predicate is satisfied, or if a stop request gets received, then it will wake up. So this is very useful for these sort of termination detection problems. All right, so with JThread, we no longer need our little side channel for signaling termination, the stood atomic that we had earlier. Now we can just pass a worker thread function that takes a stop token, and then in our while loop, we just poll on whether the stop token has received a stop request. And if it hasn't, then we just keep on doing work. All right. So next, let's go build the multi-consumer, multi-producer queue that we're going to use to distribute work items to the worker threads. So we're going to build a bounded multi-producer, multi-consumer queue, not because a bounded queue is better, but because it is the canonical example of the next concurrency primitive that I want to introduce you to, which is semaphores. So a bounded queue means that there is a fixed number of entries that can be in the queue at any time. And if you attempt to enqueue into the bounded queue and it's full, then you have to block until an entry becomes available. So the upside of a bounded queue is that it has a fixed resource footprint. The downside is that you have to potentially block when you enqueue. An unbounded queue has the upside that you don't need to block to enqueue, but it has the downside that it has an unbounded resource footprint. If your system ends up massively oversubscribed and everybody's just submitting work to the queue, well, the queue is going to grow really large. But as I said, we're just going to talk about a bounded queue today because it is a better example of what I want to show you. So we've got this concurrent bounded queue class. It takes a template parameter, which is the queue depth. So the invariant of this queue is that at most queue depth objects are in it at any time. So we have a stood queue that stores the actual items. Then we have a mutex that will protect access to that stood queue. And then we have 2 semaphores. So what are semaphores? Semaphores are synchronization primitives that limit the number of entities that can access a shared resource concurrently. A counting semaphore is a semaphore object that models like a non-negative resource count. So something like a mutex is a specialization of a binary semaphore, or a semaphore that can have a count of 1 at most, right? Because a mutex allows one thing to have access to a resource at the same time, whereas a semaphore allows n things to have access to a resource at the same time. The other difference is that a mutex has thread identity. So the guy that locked the mutex has to, like the thread that locked the mutex has to be the thread that unlocked the mutex. And I just said guy there, and I shouldn't have said that, but I too am bad about that. So pretend I said person, or thread, whatever I should have said. So where was I? Yes, so the difference between a mutex and a semaphore is also that a mutex has the notion of thread identity. So with a binary semaphore, one thread could lock it and another thread could release to it. You can't do that with a mutex. We'll talk more about things that have thread identity later. So this is what the counting semaphore API looks like. So you've got a release method that increases the count that the semaphore has by some integer amount. Then you have a acquire method that attempts to get 1 count from the semaphore in blocks if no count is available. And then you have a number of polling interfaces of the try underbar variety. This is a fairly common pattern in the standard library. Mutex has these types of non-blocking interfaces, as does condition variable, etc. And the other thing about counting semaphore is that it takes a maximum possible value. This is useful because on some platforms, if you know, for example, that the count of your semaphore will never be greater than 32 bits, there might be some operating system primitive or some hardware primitive that you can use to implement this. Whereas if you always needed to support, a 64-bit counts, you would have to do something slower. All right, so that's what semaphores are. So there are 2 semaphores in our concurrent bounded queue. The first one is called items produced. This represents the count of how many items are in the queue right now. So it starts off as 0 because initially the queue doesn't have anything in it. Then we have the remaining space semaphore, and that is that represents how many slots are available in the queue. How many like free entries are there? How many times can I push something into the queue? That starts off as queue depth because originally the queue is empty, so we can put up to queue depth things into it. So now let's look at how we actually implement this queue. There's one helper method and then an enqueue and a dequeue function. So we'll start off with the helper method, which I just call pop. Pop just takes a lock on the items mutex and then takes the first item out of the queue. It looks more complicated than that, but that's only because stdqueue has a sort of terrible pop API in that pop doesn't actually return you the object that you popped out. So first you have to go move the object out, and then you do pop, and then you go and return the thing that you moved out before. But so pop just takes it just locks the queue and takes the top item out of the queue. Yeah, that's what I just said. All right, so then we have our enqueue method, which takes some object and puts it into the queue. So the first thing we do is we have to make sure that there's enough space in the queue for us to put the object in. So we acquire on the remaining space semaphore. This will block until it is able to get to decrement that semaphore, to get a count out of that semaphore. So then once we've acquired a space, once we know that there's an entry in the queue that we can put this thing into, we now need to go and actually enqueue it. And we do that by just locking the items mutex and placing the item in there. Now, you might think, well, why do you need the mutex here if you've got this remaining space semaphore controlling access to the queue? Well, the problem is that, let's say we've got 8 threads, and they're all trying to put items into the queue. Let's say that there's 4 slots available in the queue. So 4 of those 8 threads will successfully acquire, and they might do it at the same time, and then they might all concurrently be attempting to put an item into the queue. And so you still need to lock this mutex to ensure that nobody is trying to push things into the queue at the same time. The benefit of having the semaphore here is that the 4 of those threads that didn't acquire successfully from the remaining space queue, they will just continue being blocked until space becomes available, instead of them waking up and also trying to put something into the queue and then like finding out that there's no space only after they've acquired the mutex. So this is a little bit lower contention to do it this way. And so then finally, after we've actually put the item into the queue, we need to let anybody who's trying to dequeue an item know that there's some new item available to them. And we do that by releasing to the items produced semaphore. And then somebody who is attempting to acquire from the items released semaphore to enqueue will see that and will wake up. So next, let's look at dequeue, the other end of this. So in dequeue, the first thing we do is we attempt to acquire from the items produced semaphore, the one that we release to at the end of the enqueue method. Once we've acquired from the items produced semaphore, we know that there is an item in the queue that we can take. So we have an invariant right here that the queue is not empty at this point. And so then we go and call pop, which, as I said before, blocks the mutex and takes an item out of the queue. And then, now that we've taken something out of the queue, there is some free space in the queue. So we need to signal to anybody who's in queuing that, hey, there's some free space, you can go put something into the queue. And we do that by releasing to the remaining space semaphore. All right, and then here's what try dequeue looks like. It's basically the same as dequeue, except instead of calling acquire, it calls try acquire. And instead of returning a T, it returns an optional of a T. And so if try acquire fails on the items produced semaphore, then it just returns immediately. So this is the non-blocking version here. If there's nothing in the queue, then try dequeue will just return an empty optional. All right, so let's look at how we can improve how this little bounded queue will perform under contention. Right now, we're using a stood mutex. Stood mutex is a fairly heavyweight synchronization primitive. It's typically implemented with some sort of OS synchronization primitive. That usually means that you have to make some sort of syscall to use this thing, and typically there's some amount of OS thread suspension involved here. Now, most implementations will have some sort of atomic-based fast path in their mutex implementation to avoid always calling the OS synchronization primitive. The reason for that is because these OS synchronization primitives, while they tend to be very fair, they also tend to have very high overheads and to be fairly high latency. That's not always the right option. Like something that's fair but higher latency isn't always what we're looking for. So let's see if we can come up with something that's going to be lower latency, and then we'll try to strive for something that's going to also be pretty fair and perform pretty well under contention. But let's start off with something really naive. We'll implement spin mutex. And spin mutex is just going to be a thing that has an atomic flag, and the way that you lock this is you just attempt to set the flag to be true. So you try to cast in the flag to see, hey, was it false before? And then if it's false before and I've set it and I'm the person that set it to true, then I've acquired the lock. And we just keep doing that in a loop until it succeeds. And then to unlock it, we just set it to be false. So the pros of this is pretty low latency. It's just going to use atomic flag, which is guaranteed to be lock-free on all your platforms. It's not going to call into the OS. It's not going to do anything particularly expensive. But it has a bunch of cons. So it's going to be pretty poor under contention. If you have like 200 threads, all of which are attempting to lock this mutex at the same time, that's going to be pretty terrible. And it's unfair. We'll talk about fairness a little bit later. But the biggest problem here is that this does busy waiting. So this while loop right here, we'll just enter this loop and we will stay in this loop actively polling on this atomic until we succeed. And we will not yield the core that we're using to some other thread. We'll just be on that core and pounding this atomic until we get it. So that's going to be pretty energy inefficient. It can be pretty unfair. This is just not a particularly optimal approach unless you're in like a really weird environment where you have, very few cores. So you don't care much about the fact that this is poor under contention, and you have complete control of the hardware. So you don't care about anything else that's running on the platform. You're just the only one running, so you don't care if you are being unfair to other processes. So let's look at a slightly better version of this, which uses what we call exponential back-off mechanisms. The idea here is that if you've failed to set the atomic repeatedly, then you start yielding or sleeping to other threads for a while instead of spinning to avoid contributing to contention issues. And the longer that you've gone without successfully acquiring this atomic, the longer or the more heavyweight of a sleep mechanism you use, with the idea being if I haven't acquired this, quickly, then like a lot of other people are trying to acquire this, and I should wait for a longer period of time here. That's the exponential part here. That the longer you go without successfully acquiring this thing, the longer you will wait after each unsuccessful acquisition. So this is the x86 Linux version of HPX's exponential back-off mechanism that I just copied from our production code base. So we still have the same like while loop that we had before, just this time we're keeping track of how many times how many iterations have we been in that loop, how many times have we tried and failed to set the flag. And for the first couple times, we just keep trying without any back-off mechanism. And then if it's been like between 4 and 16 times, we try some sort of processor yield. This is the sequence for doing that on x86. And then if it's been between 16 and 64 iterations, we'll call schedule yield, which on Linux tells the OS, hey, I'm this thread, and I just want you to go put me at the end of your queue of people that get access to cores. Go let some other thread run. And then finally, if we've spent more than 64, we've done more than 64 attempts to set this atomic and we haven't succeeded, we just start sleeping for 1,000 nanoseconds. And the unlock mechanism is the same as it was before. We just call clear. So this approach is actually pretty good. If you tune something like this for all the platforms you care about, this can be pretty great under contention, and it'll be super low latency. But the problem is, who wants to write this code? Like, this is just one platform's code path. You have to go write this for all the platforms you care about. And the other thing is, these numbers here, like 4, 16, 64, those are just numbers that I randomly picked in 2013. I don't have any idea whether those are the best numbers. We just picked them. They're just magic values. How are you supposed to figure that out? Well, in C++20, you don't have to, because we've added a polling mechanism to atomics. So in C++20, you can wait on an atomic, and then you can notify on the other end of an atomic. So the way that this wait API works is you say, I want to wait until this atomic's value changes to no longer be this. So when I do flag.wait here, on what flag.wait true here, I'm saying, wake me up when the flag is no longer set to true. And then the unlock side of things, once we've changed the value of flag, we call notify1, which will do the actual notification of anybody who's waiting. So this is not just an atomic flag API. This is also an API on just stood atomic in general. So here's what the API looks like. So as I said, there's the wait, where you give it the value that you want to wait until it's changed from that value. So if it's already changed when you call this function, then wait will return immediately. Then there's notify1 and notify all. These are similar to the condition variable notify function. So notify1 will wake up one person who was waiting for the value to change, and notify all will wake up everybody who was waiting for the value to change. So the interesting thing about this API is that it does not necessarily have to be implemented with exponential backoff. There's actually a number of different options that your implementation has, and that's a good thing because it means that instead of you having to figure out what the right thing to do is, your implementation has a great deal of freedom in picking an answer that's correct for the platform that you're on. So let's look briefly at what some of those options are. So here are some possible implementation strategies. You could, and these are also implementation strategies that are supported in the the pending libc++ implementation that my team is in the process of upstreaming. So you could implement this with futexes, which is an OS synchronization primitive. You can do this for certain size objects on Linux and Windows. You could implement this with OS condition variables supported for certain size objects on Linux and Mac. You could use a contention table with either of those two approaches because, as I mentioned earlier, OS synchronization primitives tend to be fairly heavyweight to construct and to use. So having some mechanism to amortize the cost of these is pretty useful. If anybody's familiar with the idea of a lock table, which can be used to implement non-lock free atomics, it's basically the same approach here. You could also implement this with, as I said, with timed exponential backoff. That will work pretty much on every platform. And if you don't have some clever way to do this, you could just implement this with a spin lock, where the wait side of things just spins and the notify side of things doesn't actually do anything. And in fact, if your implementation takes the timed backoff approach, then your notify methods on that implementation won't do anything either. That doesn't mean that you should not write them, though. It might work on your platform, but then you move to another platform and things blow up. So don't forget to write notify. Somebody will have to write a thread sanitizer check for that or something. So this is another little addition in C++20, which is that atomic flag has had the test method added. I didn't find a way to work that into the demo, but I just want to mention it because it's kind of ridiculous that atomic flag, there wasn't a way to just test it before C++20. You could only test it and set it. This is a little tragic. So atomic flag is now slightly more useful. Although me personally, I'm just going to keep using atomic bool because it makes more sense to me. All right. So there's still a problem with this mechanism, which is that while it's good under contention, while it's low latency, it's not a fair mutual exclusion mechanism. So let's say we got two threads, thread A and B, and thread A starts trying to lock this mutex. And while thread A is locking this mutex, it's entirely possible that thread B could come in and that thread B could just happen to win. That for whatever reason, thread B happens to be the one that acquires the atomic before thread A. But the problem is thread B actually started locking this thing after thread A did. So thread A was like in line, and then thread B came in and cut in line. And thread A is like, hey, that's rude. Like, I was here. I was waiting. Like, you should have waited your turn. So the problem, again, is that the mechanism that we have right now, that we just talked about, is unfair. And we would like something that's fair. So one approach is to build what's called a ticket mutex. So the idea here, we're going to have two atomic accounts. One we're going to call in, and one we're going to call out. Here they are right here. So when we go to lock this thing, first thing we're going to do is we're going to do an atomic increment on in. And we're going to get back some number from in, some number that's going to be unique to us. We're just going to ignore like wraparound and stuff like that. So we're going to get some number by atomically incrementing in. We know that that number is unique. Then we're going to go into some polling loop. And in that polling loop, we're going to load the value of the out atomic. And we're going to check whether that out atomic, whether the value that we just loaded, whether that's equal to the number that we got. And if it is, then we're going to return because it's done. We know that now it's our turn, and we've locked the thing. But if the number of out is not equal to our number, then we're going to wait for out to change, and then we'll try again. On the unlock side of things, it's pretty simple. All we do is we just increment out by a count of 1. And then we just notify everybody who is waiting on this, who might potentially have that number. So I don't know if this cultural reference will make sense in this country, but in the US, when you go to a grocery store and you want to order something at the deli counter, they have some sort of ticket system like this. And so instead of waiting in a line, you go up and you take a number, and then there's some sign that says what number they are on. And when your number gets called, that's when you come up. And this means that instead of waiting in line, you can go do some other shopping and come back later when your number is closer to being called. So that is why this is called a ticket mutex. So this is nice because this is a fair, low latency synchronization primitive that performs pretty well under contention. So there's one more thing that we can improve here. We don't want these two atomics to live on the same cache line, because we do not want people who are getting new ticket numbers to be contending with people that are polling on out. So if I'm coming in and I'm just trying to get a new ticket number, I shouldn't have to I shouldn't be affected by anybody who is in that while loop there trying to read the value of out. So what we need these two things to be on separate cache lines, and this is actually a C++17 feature. We can figure out what we should align these atomics to using this helpful, I believe now, inline const expert value, stood hardware destructive interference size, which I know is a very unfortunate name. You can blame JF Bastion for that. And so what hardware destructive interference size typically is like the size of your cache line. It's a value which is large enough that if you align two objects to that size, then you should be ensured that there will be no destructive interference at the cache level when you're trying to access these two things. All right, so going back to our concurrent bounded queue, we did all of that so that we could change stood mutex to ticket mutex here, and now we have a slightly better queue. Okay, so now let's go talk about our termination detection mechanism. So now we're going to sort of put all of the pieces of this thing together. So we're going to assemble this bounded depth task queue class. It will have a concurrent bounded queue that has pretend instead of any function, any invocable here, it says stood function. Any invocable is just a name for a better version of stood function that is friendly to move-only function objects. So we've got a queue of function objects, and then we've got a group of threads, so our actual worker threads. And so then we've got this process task function here, and this process task function is the function that each one of the threads in that thread group will execute. It's very simple. Well, it's very simple right now. All that they do is, while they've not received a stop request, they dequeue items from the task queue and they execute them. That's why there's two parentheses here, or two sets of parentheses here. The first set is for the function called the dequeue. Then the second set is calling the call operator on the function object that was dequeued. And then in the constructor for this class, we just call the constructor for the thread group class, and we give it the process tasks function as the thread function for it to execute. All right, then we've got our submit function here. Submit just calls in queue on the task queue. And that's pretty much it. That's our API for now. So let's take a look at how we'd use this thing. So I've got some atomic count here that I've just got to play around with. And then I create a bounded depth task manager that has a queue limit of 64, give it 6 threads. And then I go and I submit 256 tasks to this little thing that increment this atomic account. So there is a bug here, though. And the problem is that the workers may receive a stop request and exit before the queues are actually clear. So at the end of this scope right here, the bounded depth task manager gets destroyed. Then the thread group class gets destroyed. And then the JThreads get destroyed. And when the JThreads get destroyed, they join with their parent threads. And when that happens, they send a stop request to those workers, which means that those guys see that stop request. And they're like, OK, we're done. Like, we'll just stop processing tasks right now. But there's nothing in that process that ensures that there's no work left in the queue. So you might get an answer of like 128 instead of 256 in the print line here. So what we need to do is we need to ensure that when we get the stop request here, we need to make sure that the queue is cleared before we finish. And so the way we'll do this is we're going to add another loop to process tasks, which is just going to be a loop that will do while true, and then we'll break inside of it. And what we'll do inside of that loop is we will keep trying to dequeue stuff from the tasks queue and executing those things. And then once we're no longer able to successfully dequeue anything else, then we know we're done and we'll break out of here. So basically, this is just a second task processing loop that we do after the first one, where the first one is we do that until we've received a stop request, and then once we've received a stop request, then we just keep processing tasks until there's no more tasks left in the queue. All right, so there's still a bug in here, and the bug is that a worker thread may block while dequeuing after all tasks have been completed, but before the stop request is received. So I'll say that again. So somebody could block while dequeuing after all the tasks have been completed, but before the stop request is received. We need to control when all the worker threads exit the first loop. Basically, when we're tearing down this system, we need to make sure that we sort of hold everybody at this line right here until we tell them that it's okay for them to move forward. And so we're going to do that in the destructor of bounded depth task manager. We're going to do it like this. First of all, we're going to create a latch. So a latch is a coordination primitive where you give a latch a count of how many things are going to arrive at this latch. And then all those things arrive at the latch, and you can either arrive without waiting or you can arrive and wait. And if you arrive and wait at a latch, then you will complete waiting when the desired number of things have arrived at that latch. So this latch will construct with thread size plus 1 threads. So we want this, we're going to have however many threads, worker threads we have, plus 1, the thread that's destroying the bounded depth task manager, are going to wait on this latch. And there's a precondition on this destructor that you better not try to destroy the task manager from one of the worker threads itself. So we create our latch, and then we submit one task for each one of the worker threads, and that task will call arrive and wait on the latch. And the trick here is, we know how many actual threads are in this task pool, and each one of them will get one of these tasks, and then it will start blocking on this latch. And so that guarantees us that no thread in the worker thread pool will execute one of these little tasks more than once, because when they get their first one, they'll be blocked, they won't go do anything else, and then each other one of the worker threads will eventually get one of these tasks. So then, at this point, we know that all of the worker threads are blocked right here. They are in a call to tasks. They're executing this task that we submitted to them that arrives and waits on the latch. So now we've held them in the place that we want. And then after that, we now go and request that they stop by calling threads.requestStop. And then we arrive ourselves at the latch. And when we do that, then all of the threads that were waiting on that latch will wake up. They will be at the end of the body of this loop here. They will go check the stop request, the stop token. They will see that a stop request has come in, and they will all exit that loop. They will go to the loop that processes any outstanding work in the queue, and then once that's done, they will exit. And so now we have a termination mechanism here that works. All right, so that's what this looks like. So let's talk a little bit more about latch. So this is what the API of latch looks like. When you construct a latch, you tell it how many things will arrive at this latch. And it's got countdown, which allows you to arrive at the latch without waiting. So countdown decrements the number of things that it's expecting to arrive. Then you've got a try wait function and a wait function which will block pending the completion of the latch. And then you have an arrive and wait function, which is sort of the common case where you want to both arrive at the latch and then block pending its execution. We'll talk a bit more about latch later. We're going to use it in a couple more examples. All right, so now let's look at another way to break our task manager. So we've got now a task that submits other tasks. So we've got this task submit tree, and what submit tree does is it's given some level, And as long as the level is not equal to 0, it goes and submits 2 children tasks, each of which has a level of 1 less than the parent task here. So we go and we create our bounded depth task manager, and then we launch one submit tree task with a level of 8, and it'll go spawn off a whole bunch of children. So yeah, I explained that. Yeah. All right. So the problem here is that this code deadlocks because when the queue is full, submit will block until space is available. We're submitting tasks that that are being executed by the worker threads, so it's possible for all the worker threads to block, and then eventually, like everybody's blocking, waiting for space to be available while executing a task. But there's no worker threads that are not blocked who can go and process tasks and make space available in the queue. So the situation we end up with is that every one of the worker threads is in some call to it's dequeued one of these submit tree tasks, and it's running one of these submit tree tasks, and it's blocked in one of the calls to submit in the submit tree task because there's no space left in the queue. So the issue here is that in our current implementation of submit, we do not ensure that the thing that we are blocking on will make forward progress. To block until there's space available in the queue, we need to ensure that space will eventually become available in the queue. The one way that we can do this is, instead of just calling the blocking in queue function, we can call try in queue in a loop until it succeeds, and then we'll call this make progress function here. And what make progress will do is it will dequeue tasks from the queue, and it will execute them, because this is a way of clearing space in the queue. And so this helps us ensure that that more space becomes available, which helps us ensure that eventually our call to try in queue will succeed. So what we're doing here is we are using the calling thread, the thread that is submitting work. We are using that thread to make progress on the work that will cause this condition that we're blocking on, space becoming available in the queue, to occur. So this technique of delegating our own execution resources to ensure the progress of things we are blocking on, this is called boost blocking. I talked about that a bit in my CPPCon talk last year, if you're interested in learning more about that. All right, so we still have a bug here, which is that we can blow out the worker thread stacks with recursion here, because we can end up in a call to submit tree that's calling submit, and then that call to submit is dequeuing another submit tree task, which then calls it submit again, and then dequeues another submit tree task. And so eventually you can run out of stack depth, but we're not going to solve that problem. It's not something that will come up in the examples we're looking at right now. All right, so this is our bounded depth task manager. So now let's look at building 2 parallel algorithms on top of this little system. We're going to start off with a parallel histogram. So the idea with this histogram algorithm is we take some input range, and then we take some output range. And we have some indexing operator, which the indexing operator takes a value in the input range, and it maps it to an index in the output range. So that is right here. So we index into the output range by calling op on the value of each element in the input range. And then we increment that entry in the output range for each input range element that hits here. So this is a way of going through a set of data and counting how many times a particular value occurs. Right, so this is the serial implementation. It's pretty simple. We just use stood for each. As a default, op could be stood identity. So if we just wanted to take some data set and say count how many times each value occurs in that data set, we would just use the identity function for the mapping function there. We would need to ensure that the output range was large enough, of course, for integers. In the range of 0 to n. All right, so now we're going to look at how we would parallelize this algorithm. So first of all, we'll change some of the requirements. One, we're going to add this execution policy parameter. All of the parallel algorithms in C++17 have an execution policy parameter. The execution policy that we're using here is a little bit more interesting. It's got a submit method, it has a make progress method, and then it has a method called concurrent agents, which tells you how many underlying threads does the execution policy have available to it. And then we're going to require that our input range be random access and that our output range be random access. So now let's look at the implementation of the parallel histogram. So the first thing we do is we need to figure out how many elements we have, and then we want to figure out the number of chunks that we're going to create, and we're going to do this based on how many concurrent agents we have. So by concurrent agents, I mean, like, let's imagine that the execution policy is backed by a thread pool. Well, that thread pool has some number of threads backing it. Those are concurrent execution agents. And so we're going to pick the number of chunks based on some, in this case, some multiple of the number of threads that we have. Now, why don't we just use one chunk for each thread? Well, we want to have a little bit of load balancing here, because, like, imagine the case where the number of elements doesn't evenly divide into the number of chunks. Then the last chunk will be a little bit smaller than all the other ones. And so then that last thread will finish before all the other ones, and then it might just be waiting idle while the other guys are doing some work. So by picking a finer granularity for our chunks, we can ensure that we have better load balancing, that there will be less time when there are threads that are not doing work. All right. So then we're going to create a latch. We're going to need a latch because we're about to create a bunch of worker tasks, and we want to know when those worker tasks are done. Then we've got some for loop where for each chunk, we're going to create a task that will compute the result for each one of these chunks. And in that task, the first thing we'll do is we'll just figure out which range of elements we're going to deal with. So each one of these chunks is going to be responsible for a certain range of the input. And we just do some math here. We have this std_min logic here to deal with the last chunk, which might be smaller than all the other chunks. And then we're just going to do the serial version of the algorithm. We'll just call for each on the range for our chunk, and we'll use the same lambda that we used before, where we do we index into output using some transform function here. And then we increment for every output element that we find, or for every input element that we find that matches a particular output indices, we increment by the value inc. Now there's a bug here, which is that different chunks may update an element in the output at the same time. So I could have, the first chunk and the second chunk, they could both hit an element that maps to the same index in the output, and then they could both try to increment it at the same time. And so we need to ensure that doesn't happen, that the increments happen atomically. Now, there's a few ways we could do this. We could use a mutex, but that's unfortunate because mutexes, as we've discussed earlier, are fairly heavyweight synchronization primitives. Or we could force our users to provide us with a sequence of std atomics as the output, because in C++ prior to C++20, if you wanted atomic access to an object, you needed to have declared that object as atomic. Things that you can access atomically with C++ atomics, they have to have been std atomic objects. That's no longer the case in C++20. We now have this useful thing called atomic ref, which provides us with atomic access to non-atomic objects. So what we can do here is we can create an atomic ref. We give it a reference to the element that we want to increment atomically, and then atomic ref works just as if we had declared that output element atomically. Now, of course, there's a precondition here that this will only work if everybody who's accessing that object is using atomic ref. If everybody who's accessing it at the same time concurrently is using atomic ref. Otherwise, obviously, it doesn't work. So std atomic t holds a t, and std atomic ref does not hold a t, but otherwise they have the same API. All right, there's one other C++20 feature here, which is we're using fetch add, which is a atomic member that is only available on pre-C++20 on the integral specializations of atomic. So this generic algorithm would only work if your element type in the output was ints. But in C++20, we now have support for floating point atomics. So there are now specializations of atomic for floating point that add fetch add and fetch sub. And on NVIDIA GPUs, we have hardware support for this. Sales pitch over. All right, then the last thing that we do in our histogram algorithm is at the end of each one of these chunks, we count down on the latch to indicate that that chunk has finished its work. And then back in the calling thread, we block on that latch, but we block with this boost blocking mechanism to ensure forward progress. So we just have a while loop where we keep waiting on the latch, and we keep calling make progress on this execution policy, which is some unspecified mechanism of ensuring that the tasks that we submitted will make forward progress using our thread of execution if needed. All right, so that's our algorithm. We're going to look at one more. We're a little short on time, but we'll probably get through it. All right, so the next algorithm we're going to look at is called exclusive scan. This is a slightly modified version of partial sum. Exclusive scan is a new algorithm in C++ 17. So what exclusive scan does is it takes a range of values and it writes the sum of the first n-1 elements into the nth element of the output. So what partial sum does is the same thing, except partial sum writes the sum of the first n elements into the nth element of the output. So exclusive scan is exclusive because it excludes in the sum the element at the nth position in the input. So we'll take a look through an example because that'll make more sense. So we've got 9 elements that we want to scan together here. So this is what the correct scanned output looks like. So for the first element, the x here is the initial value that we're passing to exclusive scan. So this initial value gets added to all of the elements. So for the first element of the output, there are no elements before the first element, so that sum is just the initial value, x. For the second element, there's the value a, there's one element before it, a, so the sum is x plus a. For the third element, the sum is x plus a plus b, etc. And then the last element is the sum of all of the elements except for the last one, plus the initial value. All right, so let's look at how to parallelize this, and it's a little bit non-intuitive how we do this. We're going to look at an approach that only works for non-commutative and non-associative operations. So the intuition here, we're going to start off by just breaking this problem into sub-problems. And similar to our approach with histogram, what each one of the sub-problems with histogram amounted to was applying the serial implementation of histogram to each one of the sub-problems. So we're going to try to do the same thing here. So we'll break this into 3 different parts, and then we will do a serial exclusive scan on each one of these parts here. And then this is what we end up with here. Assume that the initial value for each one of these exclusive scans is some like default constructed value. This algorithm only works for things that are default constructed. Limitation, we'll just ignore it. All right, so now we've got this. And so now what's the things that we're missing? So if you look at the first chunk here, the first chunk here is mostly right. If we just added the initial value x to the first chunk here, we would end up with the right answer. But then the second chunk is missing some information. The second chunk needs the sum of all the values from the first chunk. And likewise, the third chunk needs the sum of all the values from the first 2 chunks. Because, as you can see here, the middle 3 elements and the last 3 elements, though the middle 3 elements each have the sum of the first 3 elements in them, and then the last 3 elements each have the sum of all of the prior elements in them. All right, so what we're going to do is, after we've done in parallel each one of these sub-problem exclusive scans, we're going to have each one of these chunks write the sum of the value of all of their elements into some array. We'll call it aggregates. So the way that we do this, we could just call like std reduce or std accumulate, but we've already done this exclusive scan, and the exclusive scan, we know that the last element of the exclusive scan is the sum of all of the elements except the last one. So we just take the last element of the exclusive scan and the last element of the input, we add them together, and then each entry in this aggregates array is the sum of the values for each one of these chunks. All right, so now in serial, one thread goes and does an exclusive scan on this aggregates array. And this is the point at which we add in the initial value for the problem. So it does an exclusive scan with the initial value of equal to x. And this gives us an aggregates array that looks like this. And so then, now that we've done this this serial work of this exclusive scan on this aggregates array, we will now go and correct all of the values. So now in parallel, we will go and for each chunk, we will increment each one of the elements by the value in that chunk's slot in the aggregates array. And so this will end up giving us the correct answer here. In production, there would be a bit more hierarchy. We'd have more of a tree computation. So this two-pass algorithm, usually we call this first pass the upsweep because there is a decreasing amount of parallelism. And then there's a serial section. So we're computing some information, then we have to do some computation in serial and then redistribute that information out to everybody. And then the second pass is called the downsweep because there's an increasing amount of parallelism in that pass as the information is aggregated out to everybody. All right, so now let's look how this is implemented. It's pretty similar to the histogram algorithm. So we start off doing the same thing where we figure out how many elements and chunks we have, just as we did in histogram. And for this algorithm, we're just going to spawn one chunk for each concurrent agent. I'll explain why in a moment. And then we create our aggregates array, which is just a stood vector of t. And we have one t for each one of the chunks, and that's where we're going to store the sum of the values from that chunk in the upsweep pass. Then we have two coordination primitives. One, we have a barrier. For right now, just think of a barrier as being similar to a latch. And then we have another latch. And we're going to use this upsweep barrier to coordinate the end of that first pass. And we'll use the downsweep latch to coordinate the end of the second pass and the completion of the algorithm. So now let's look at the actual worker tasks themselves. So again, we've got a loop that spawns some number of tasks, and each task will deal with one chunk. And so it computes the part of the input that it's responsible for, and then it goes and does the serial exclusive scan of those input elements. And then, as mentioned, we need to compute the sum of all the input elements for that chunk and store it in the array. And we just do that by taking the last element of the exclusive scan and adding it to the last element of the input array. And then we assign that result, the sum of all of the input elements for this chunk, to the aggregates array. Then we go and we arrive and wait at this barrier. So the next thing we need to do is we need to have one thread compute the exclusive scan of the aggregates vector after all of the threads have finished the upsweep phase. Fortunately, stood barrier has a nice little facility for doing this. Stood barrier, unlike latch, supports a completion function. So a completion function is a function which will be run by one thread after the end of each phase of the barrier. So after everybody's arrived at a particular phase of the barrier, then one guy will run the completion function, and then all of the waits will complete. So let's look at the barrier API. It's pretty similar to the latch API. One of the big differences is that, again, it optionally takes a completion function when you construct it. Just like with latch, it takes a count of how many things you expect to arrive at each phase. Now, unlike latches, barriers have multiple phases, which makes the API a little bit more complicated, because if you're asynchronously arriving on a barrier and then you want to wait on the barrier later, you need some way to tell the barrier what phase you're waiting on. So whereas the countdown on a latch, which is the asynchronous API there, returns void, arrive on barrier gives you back an arrival token, and then you wait on that arrival token. When you want to wait on the thing, you have to give it the arrival token that you got from arrive. There's also a synchronous function, arrive and wait, just as with latch. And there's arrive and drop, which is the equivalent of countdown. That's when you just want to count on something and you're never going to want to wait on it later. So the comparison between these two, latch and barrier, they both support asynchronous arrival. Latch is single phase, whereas barrier supports multiple phases. Latch has no notion of thread identity, but barrier does. I'm a little short for time, so I'm not going to explain that much, other than to say that that's why we're using just one chunk for each one of the threads in the task pool, because with latch, threads may arrive multiple times within a phase, and any thread may wait on a latch. Whereas with barrier, a thread may only arrive once per phase, and only a thread who has arrived may wait. This is similar to the distinction between mutexes and semaphores. A mutex, the thread that locked it, has to be the one to unlock it, whereas a binary semaphore, anybody could unlock a binary semaphore. And latches don't support completion functions. All right, so back to the exclusive scan algorithm. So our completion function is just going to call exclusive scan on the aggregates array. That's all that it does. So after the completion function, that completion function will be run after all the threads write to their slot in the aggregates vector and come and arrive and wait on this upsweep barrier. So we have these synchronization guarantees that all the arrivals will happen before the completion function is run, and all of the waits will complete after the completion function is run. So then the second part of the algorithm is pretty simple. After the waits have completed, we know that the exclusive scan of the aggregates vector has been finished, and we can start the downsweep phase. And the downsweep phase is just a for each function that we call, where we take the aggregates value for the slot that belongs to our chunk, and we just add that into the to each element of our chunk. Then we count down on the latch, and that's it. We're done. And then back in the calling thread, we do the same thing we did in histogram, where we poll on the downsweep latch until it's completed, and we call make progress to ensure forward progress happens. All right, so that's it. That's a simple way to implement a work-efficient parallel exclusive scan. If you're interested in more about that, you can go Google that term, work-efficient parallel exclusive scan. All right, so what did we talk about today? There are a bunch of std atomic enhancements in C++20. The wait notify interface is the most notable of them. There's also atomic ref, which gives you a way to view a non-atomic object atomically. There's the new test interface for atomic flag. There's now floating point specializations for std atomic. There's std latch and std barrier, which are facilities for coordinating groups of threads. We have std counting semaphore, which is a more general mechanism for controlling shared access to resources than mutexes. And then we have std jthread, which has a joining destructor and this nice interruption mechanism. That's my talk. We are over time, so any questions, we'll have to go to whatever discussion zone they're bringing me to. Thank you all for your time.